He's also appeared on national television and for some time was a regular fixture as the science guy on a local morning talk show. He is also the co-founder and CFO of the Branched Oak Observatory. Mr. Stevenson, welcome.
Thank you very much. I'll ask, did everyone get an envelope? Did we have anyone that needs an envelope? These have your solar eclipse glasses. We're actually going to pull these out a little bit later. But really, first I'll kind of reintroduce myself, but also just mention that my wife, who also works these presentations with me, the in-laws are in town, so she decided to stay at home and give me full billing, so Kendra will not be available tonight. Again, my name is Michael Sibernson. I am a lecturer of astronomy at the University of Nebraska at Lincoln and the CEO of Branched Oak Observatory. Branched Oak Observatory is located near Branched Oak Lake and recreation area, which is just northwest of Lincoln, just a few miles. It's just about 15-20 minutes outside of Lincoln. Nice thing is, everyone in Lincoln knows Branched Oak Lake. It's a very large lake. It's a wonderful, wonderful recreation area. And if you ever find your way traveling towards Branched Oak Lake, instead of taking a right, you take a left and you'll find Branched Oak Observatory. You can follow us on Facebook, or just look at our website, branchedoakobservatory.com, and we list all of our upcoming events. And we'd love to see you out there. But before we start tonight's presentation talking about the eclipse, NASA, who trained all of us on speaking about the program, they wanted us to mention this, safety first. Viewing the unobscured sun, even for a very short amount of time, can be dangerous. And the reason why is that the lens of your eye acts like a magnifying glass, magnifies this, concentrates this, and can cause retina damage. And the kind of the scary thing here is that since we don't have any pain receptors, you can be looking at the sun and not even realize that you're doing damage. And that's why we really need to communicate this safety to everyone, but especially to kids. And that's why we handed out our solar eclipse glasses. A very important point that I don't think that a lot of people realize is that the entire eclipse, so we're talking from this point to this point, lasts about 3 hours. 3 hours. Totality, even if you're in the center of the path of totality, is only 1.5% of the entire eclipse. So you need to wear your solar eclipse glasses for 98.5% of the time. That's if you have an optimum view of the eclipse, if you're right on the path of totality. If you are outside of the path of totality, like Omaha, you need to wear them 100% of the time when you're viewing the eclipse. It's funny, a lot of times I'll hear people say, oh, when the eclipse happens, I put on the glasses. Well, that's true, but I think they're thinking totality. Actually, during totality, if you are on the path of totality, or within that path, that's the point in time that you take the glasses off. You can actually enjoy totality with the unaided eye. And we'll be talking more about safety. We'll be talking more about that here momentarily. But I just wanted to just kind of get that out of the way. 38. This is a magic number. It was a different number yesterday. And it will be a different number tomorrow. And I imagine you can probably guess what this is. 38 days until the eclipse. I've been waiting decades for this. When I worked at the NASA Nebraska Space Grant, I called my boss into my office and I said that we've got this coming in a number of years. We need to start planning for it now. We didn't do it at that moment, but we did get a block of rooms in Grand Island for the eclipse. This is known as the Great American Eclipse because it is, in a way, it's kind of for us. The path of totality is going right through the United States, but I like to call it the Great Nebraska Eclipse because not only is the path of totality going diagonally through the United States, it's going diagonally right through Nebraska. If you are outside of the path of totality, you really do not need to travel very far to get inside of it. Just probably 20-30 minutes at most, and you'll be within that path of totality. August 21st, 2017. Now, for an eclipse to happen, a lunar eclipse or a solar eclipse, 3 things must take place. One, it must be what's called eclipse season, and I'll explain what eclipse season here is in just a moment. The moon must be in the correct phase. Actually, it's not the phase. The phase is a function of where the moon is in its orbit. So the moon has to be in a correct placement in its orbit. But sometimes it's just easier to say the correct phase. A full moon or a new moon, depending on whether it's a solar or a lunar eclipse. And three, the viewer must be in the right place at the right time, particularly for a solar eclipse, not so much for a lunar eclipse. So let's go to just kind of basic astronomy 101. I'm sure everybody here already knows this very well. At any given point in time, half of the moon is illuminated. At any given point in time, half of the Earth is illuminated. That's because we have just one lighting source. We have the sun. So half of the moon is illuminated at all times. Half of the Earth is illuminated at all times. Why is it then we see different phases of the moon? Sometimes we see no illumination. Sometimes we see over half of it illuminated. How can that be when half of the moon is illuminated? Well, it's because of the angle in which we are viewing that one half illumination. Sometimes the moon comes up in the east with the sun. That's a new moon and it's lost in the glare of the sun. Sometimes the moon is coming up right when the sun is going down. It's on the opposite side of the Earth, and therefore we have a full moon. New moon, you can't even see it, can you? New moon and a full moon when it's on the opposite side of the Earth. So this is what you would see if you were outside floating above the Earth, floating above the northern pole looking down. This is what you would see, or, well, this is what you would see if you were on Earth looking at this particular point or this particular point. When it's at a right angle, depending on what side is being illuminated, you'll see a first quarter or a last quarter. Sometimes it's called a third quarter. I prefer last quarter because it's a little bit easier to remember, first and last. This is not a half moon, like a lot of people sometimes say. And then in between these we have waxing crescent, waxing gibbous, waning gibbous. Waxing meaning that it's getting fuller and fuller, going towards full moon. Waning meaning that it's going towards a new moon. And then a waxing crescent. So a question that people commonly ask is that if we have a new moon and a full moon once every month, sometimes you have a couple full moons in a month, why do we not have a solar eclipse and a lunar eclipse every single month? Well, for the lunar eclipses, it's actually pretty close, but it doesn't quite happen. Well, I think the reason comes from a few misunderstandings. One is this illustration here is terrible. One, the moon's far too big. It should be how much? Quarter of the size of the Earth. And two, it's far, far too close. This sometimes comes as a surprise to people. The moon is 30 Earth diameters. 30 Earth diameters away from the Earth. So when you add these two together, we have 60 Earth diameters for the entire orbit. And then you'll notice that there's a little bit of a tilt there. It's actually about a 5-degree tilt. So if we were to look at it straight down on the orbital plane, and we're looking straight down at the Earth here, it looks like the moon falls within the shadow of the Earth falls within the shadow of the moon once, or well, one solar eclipse, one lunar eclipse every single month. But when we look at it from the edge, we see what's actually happening. It misses. It misses most of the time because of this slight tilt. If there wasn't this 5-degree tilt, it's true, we would have a lunar eclipse and a solar eclipse every single month. That would be pretty wonderful. Sometimes things line up just right. And then we have our lunar eclipse or we have our solar eclipse. So the first constraint is that it must be eclipse season. Eclipse season is when some technical words here, the ascending node and the descending node of the moon's orbit are aligned. I'm going to do a double Spock. This is like a Vulcan handshake here. We've got the plane of the Earth, we've got the lunar plane here, they have to intersect. And then we have this line of, it's called the line of nodes. And here, as opposed to here and here, we have eclipse season. That does not mean you will have an eclipse though. It must be an eclipse season, but it does not mean you'll have an eclipse. The second thing must also take place. The moon must be in the correct phase. In other words, it must be in the correct place in its orbit around the Earth. So it must be either a new moon or a full moon for us to see a total solar eclipse, or any type of solar eclipse, or a lunar eclipse. So let's take a look at these two. Now first, we have here a lunar eclipse. During a lunar eclipse, the moon is falling within the shadow of the Earth. And you'll notice the shadow of the Earth is very large because the Earth is very large. The moon just swims within that shadow because it's so small. Because of this, during a lunar eclipse, you can be anywhere on the Earth. If the moon is visible, you will see a lunar eclipse. Not so with the solar eclipse. You have to be in a very specific location to see that solar eclipse. During a solar eclipse, the moon is casting a shadow on the Earth. So in this case, the Earth is passing through that shadow, or more precisely, the moon is traveling across and casting, almost dragging that shadow across the Earth. And you have to be right within that small, tiny path here, this little darker area. You see, there's a darker part of the shadow and a lighter part of the shadow. I can even show that with my hand here. Let's do it over here. I can do shadow tricks here too. Now I know since we don't have the light out, it's hard to see, but you'll see there's a darker part of the shadow and there's a lighter part of the shadow. Do you see that? There's a gray kind of ghost image around my hand, and then there's a darker area. The darker area is the umbra. The lighter, grayish part of the shadow is the penumbra. And depending on where the moon is within the penumbra or the umbra, depending on where you are within the penumbra or the umbra, you will experience one of the three different types of lunar, one of the three different types of solar eclipses. For a lunar eclipse, and I know we're here talking about solar eclipses, but I thought this would be good to talk about anyway. If the moon is within the penumbra only, you have a penumbral lunar eclipse. This almost happens every single month. Almost happens, because that shadow is so large. But because of that tilt, it doesn't quite make it. The thing about a penumbral lunar eclipse is that most people wouldn't even notice it was happening, because the brightness of the moon just wanes a little bit. It still looks like the moon. It still looks like a full moon, but it just wanes a little bit. It's not quite as bright. If the moon dips its toe within the umbra, then we will have a partial lunar eclipse. And this is where it looks like Cookie Monster's taking a bite out of the cookie. It starts to disappear more and more. It depends on how far in. It might just dip its toe into the umbra. It might get 80, 90% within the umbra. The thing is even during a partial lunar eclipse, many people don't even notice it's going on unless maybe the weatherman said something. Does anyone see why? Because if you were to look up and you saw this, it's a phase. Yeah, most people think it's just a phase and they just don't even think about it. During a total lunar eclipse, you probably think it's going to completely disappear, but something very interesting happens. If the moon falls completely within the umbra, it gets dark, but then all of a sudden it re-illuminates, and it becomes this deep reddish orange. Sometimes they're called blood moons. And the reason why is that the sunlight, which is on the opposite side of the Earth, is funneling through Earth's atmosphere like a fiber optic. All the short wavelengths are being scattered, Rayleigh scattering. The longer wavelengths are allowed to go through, and those red wavelengths, those red longer wavelengths illuminate the moon, and we get this reddish orange color. And this can change depending on temperature, humidity. If there are any fires going on at the time and adding dust to the atmosphere, it can look even redder. And it really is beautiful. So we have our three different types of lunar eclipses: total, partial, and penumbral lunar eclipses. We do not have the same three for solar. It's a little bit different. Oh, by the way, here's a very nice picture that I took from a few years ago. You can actually see the moon being eaten away and then all of a sudden re-illuminating again. and then going back to full. That's during a total lunar eclipse.
Excuse me.
Yeah.
Is what you described sometimes called a moon illuminated by earthshine?
Earthshine is a little bit of a different animal. If you go outside,
I saw one this last spring. And,
if you go out and look at a new moon, or maybe a crescent moon, and you see the crescent, but you can also see the part that you normally don't see. You know, the part that's dark, but you can see it pretty well. That's Gegenschein, that's earthshine. So the light is bouncing off of the moon, off the thin sliver, bouncing off of the earth, and then going back to the moon again and illuminating it. That's why it's called earthshine. And so sometimes if the conditions are right, that part that you normally can't see becomes much more illuminated. So here we have the moon in a new phase. Remember, it has to be in the correct phase. Here we have the moon in a new phase, and we have our penumbra and we have our umbra. We have this tiny, tiny, thin sliver of that dark shadow. The viewer must be in the right place at the right time. If you are not within that little tiny sliver, that umbra, and you are within the penumbra, this is what you'll see. So even during a total, I'll put quotes on it, even during a total solar eclipse, you may not see totality. And here in Omaha, you will not see totality. It's actually pretty close, like 98%. But it's the difference between night and day. That's kind of a pun, but it's true here. You really need, if you can, you really need to pack your bags and head south to see totality, because there is a huge difference between seeing the sun almost completely covered and completely covered. Completely different experience. Depending on how close you are to the path of totality, you will see a more and more and more covered sun. The moment you step within the umbra, that's when you will have a total solar eclipse. Notice we skipped the penumbral. Remember the penumbral lunar eclipse? There's no such thing as a penumbral solar eclipse. If you're within the penumbra, you see a partial eclipse, not a penumbral. If you are within the umbra, you see a total solar eclipse. So the third type, an annular, is when the moon, so here's our total. When the moon's orbit, maybe the moon is in perigee or close to perigee. But if the moon is in apogee, it's in its furthest placement from the Earth, its angular size will be a little bit smaller. You know, if I get close to you, I look large. As I move away, I get smaller and smaller. If the moon is in apogee, the moon is about 1/2 degree. If you hold up your pinky like this at arm's length and close one eye, your pinky is about 1 degree. So believe it or not, and I know this will be hard to believe, a full moon is only about 1/2 a pinky. That's it. The sun is about 1/2 degree as well. Even though it's bigger, because it's so far away, its size is about 1/2 degree. So usually they line up very nicely, but not during this point. If the moon is at apogee, it's not big enough to cover the sun, and even if you are right in the center of the path of, well, pseudo-totality here, you're going to see this. So when I say annular, I don't mean annular, I mean, or an annual eclipse, I mean an annular, as in geometry, this is called an annulus, this ring here. But this isn't what we want. This is what we want, a total solar eclipse. The moment the moon covers the sun, that's when it gets dark. The rest of the time, it's going to be nearly imperceivable until it's in 95% covered. Then you're going to start noticing it getting darker and darker. But it isn't until it's completely covered, that's when it gets much darker. Not nighttime dark, but it gets much darker. You will feel that shadow like a ghost. You'll feel that shadow passing over you, and you'll feel a temperature change. Animals will start making noise, wonder what's going on. And you'll have this kind of sense of surrealism, because it really is. It's almost a transcendental effect. It's really absolutely incredible. And it will only last, depending on where you are, seconds to 2.5 minutes, depending on where you are. And it will be the fastest 2.5 minutes you've ever experienced. And then you'll have another about hour and a half of a partial eclipse. During this time, this is when you can take off your glasses. You have to take off your glasses. You have to be careful, of course. You don't want to take them off too soon. You don't want to forget to put them back on again. But you need to take off the glasses because you won't see it. If you've already looked at the glasses, you put them on, you can't see a thing. The only thing that you'll be able to see with those eclipse glasses, by the way, you can safely look at the sun anytime with these. Just be careful that you always have those on. You'll be able to look at the sun, and you'll be able to look at maybe the filament of an incandescent light bulb. That's about it. Everything else, you won't see it. And during this, you won't see it. You'll have to take off those glasses. And during this time, now we can see the outer atmosphere of the sun, the corona. This is the only time you will be able to see the corona with the unaided eye. And maybe, it really depends on the size of the moon, you might be able to see the chromosphere. And that's going to be on the very, very, very edge. And then these here, a lot of people like to call them flares. These are not solar flares. These are called solar prominences. So you may see the chromosphere, you may see solar prominences, but you will see the corona. And we can't predict what that's going to look like because it's kind of a living, organic thing. It's always changing. You'll get a chance to see it on that day if you are within the path of totality. So as we mentioned, the viewer must be in the right place at the right time. These paths, this is between 2001 and 2025, these paths of totality are in very different locations, very different thicknesses. Ours is about 70 miles thick. Sometimes they're hundreds and hundreds of miles thick. Sometimes they're short, sometimes they're longer. Sometimes they start right in the middle of the ocean, sometimes they end in the middle of the ocean. Some people, of course, have the ability to, and the means to maybe fly and see an eclipse, or take an aircraft, or take a cruise ship. But for most of us, this might be it. This might be one of our only opportunities to see it. So before we talk more about being at the right place at the right time, let's answer a question that invariably I'm asked when I do radio interviews, and just people on the street. Are total eclipses rare? Yes. And no. See, the problem is that people hear contrasting things. They'll hear, this is the first eclipse in 99 years, almost 100 years, and then you'll turn around and you'll hear someone say, well, there's a total eclipse every couple years. So what's the truth? It depends on how you ask the question. You have some type of solar eclipse. Some type of solar eclipse. Partial, annular, total, 2.5 times every year. 2.5 times every year on an average, A total solar eclipse happens somewhere on the Earth once every 18 months. So about 1.5 years. Every 1.5 years, a total solar eclipse happens, but the thing is, you have to be in the right place at the right time, and that's just it. If I stood right here and there was no building around me, I would have to wait, on an average, about 400 years. So the odds of you seeing an eclipse right where you stand is about 1 in 400. So this is, for many people, a once-in-a-lifetime event. Yes, there is another total solar eclipse happening in 2024. But we will not see totality. We'll need to get up and move to see that. The last total solar eclipse visible in the contiguous United States was 1979.
I remember that.
And so probably a number of people remember this. This one, if you were to see totality, you'd need to be in the northwest. So many people probably saw a partial eclipse. Many people remember it probably just saw a partial eclipse. But they saw all the advertisements and the news reporting on totality. Here's where that 99 comes in. The last total eclipse that transversed the entire United States was 99 years ago. So this is the one that newspaper articles love to pick up because it sounds more interesting. The last total eclipse visible in Nebraska was 63 years ago, but the thing about this one, the eclipse started in Nebraska, and it was in the upper east, and then it traveled right outside of the United States. The next total eclipse visible in Nebraska is in a little more than 1 month. August 21st, 2017. So here we have that path of totality. And as you can see, it goes diagonally right through the United States, and it goes diagonally right through Nebraska. Unfortunately, Omaha is right here. Yeah.
Now your map has kind of a gray area, then a thin blue line in the middle.
Anything within this here
Okay.
would be the path of totality. I think this is just the center line. So what, ideally, you try to get on that blue line, and then you'll get the longest amount of totality. Actually, we're going to look at Lincoln here in just a moment, and I'll show you something kind of interesting about Lincoln. Here we can see the penumbra, and in a moment we'll see the umbra. There it is, traveling right across the United States.
What's the total length of time from one coast to the other?
This is just hours. It's now that's for the path of totality, mind you. The entire eclipse for us lasts about 3 hours, and that's about the amount of time it's taking to go across the United States. It is traveling at over 1,000 miles an hour. Now, I just wanted to mention very quickly, one more time, that everyone in the United States, everyone in North America will see a partial eclipse. That's how big that penumbra is. But only those that are right within the path of totality will see and experience a total solar eclipse. So here we have Nebraska. We have a number of wonderful events. We'll mention just a few of those. Let's talk about Lincoln here. The start of the eclipse is at 11:37. When I say the start of the eclipse, I mean this point here, when they kiss each other, not totality. Start of totality is at 1 o'clock, 1:02. Length of totality is 1 minute 18 seconds. This is in the middle of Lincoln, right in the middle of Lincoln. Let's go ahead and zoom in, because I just want to mention something very interesting here. These times change dramatically. I'm going to say this is the shadow here. We always see these lines, right? The path of totality. But the shadow is actually circular, kind of an oval, funny looking oval. Depends on the altitude, depends on even the shape of the moon. So it's kind of a funny looking oval that's traveling along. The closer you get to the center, the longer that totality is going to be. In North Lincoln, you would be right here, and you would see just seconds. But you see, as you travel downwards, look at how long that stick gets very quickly. And if you are in southern Lincoln, you will see actually almost 2 minutes if you're in southern Lincoln. So a huge difference between a few seconds and a few minutes just by going from one part of town to the other part of town. But then it slows down because this area, or this length here, doesn't change as fast. And so you have to travel 10, 20 miles to squeak out just a few more seconds. And if you're right on that path, you're going to see about 2 minutes, 35, 36 seconds, depending on exactly where you're located. Beatrice, Nebraska, Homestead National Monument is very close to Beatrice, and this is one of the official NASA sites. There are a number of different activities going on throughout the entire United States, but this will probably be the biggest. Tens of thousands of people will be there.
Yeah. We will be there with our radio station.
Awesome. And the Prairie Astronomy Club, well, the members that want to do it. See, astronomers are kind of funny. When you ask astronomers what you're doing, you have the astronomer who is very much into public education, and they all are into public education, and they're going to be at these different major events with telescopes set up. to view safely the sun. But then you have the astronomers that are like, I give my whole life to the public. This is the one time I want to have a little privacy, and then they'll go out in the middle of nowhere where nobody knows where they are, so they can just sit back by themselves or maybe with their family and enjoy. And it's just something that you need to decide on your own what you're going to do. So in Beatrice, you're talking 2 minutes 34 seconds. 2 minutes 34 seconds. You can see the start of totality is the same time as Lincoln. It's just because it's south of it. But the length of totality is much greater. Well, Southern Lincoln about 2 minutes, Beatrice 2.5 minutes. So boy, you're really paying a price to get 30 more seconds, but it is worth it. I will be in Grand Island. There's a major event at the Stern Museum. Probably won't be as big as Homestead, but I think there'll be thousands and thousands of people there as well. And you will see our start of totality is 4 minutes earlier. The path of totality is going from this direction to this direction. It's going from west to east. Now we'll see if our audio stands up. This is from the last one that was 1979. Just wanted you to hear what they were saying at this time period regards to watching the event.
A total eclipse of the sun, visible today over North America for the last time in this century. This is an ABC News special. Live coverage of the solar eclipse. Now from New York, here is correspondent Frank Reynolds.
Good morning. This is indeed a special events broadcast of a genuine special event. Well, we're praying for good weather, of course, along the path of the eclipse. We appear to have it by and large. We have correspondents and cameras in Oregon, Washington, and Montana. We're on the ground. We're on top of Mount Hood. We're in a plane over Portland. And the best place for most of you to see the eclipse, and the safest, is where you are right now, in front of your television set.
No. This is not what you want to do. And, you know, for many years, and I haven't heard it as much this time around. I've heard it a little bit, but I haven't heard it as much. But in the past, there was this thought that during an eclipse, it was even worse to look at the sun. You know, it's bad to look at the sun anytime, right? Except during totality. But they kind of led you to believe that there were deadly eclipse rays that made it even worse than it normally is. So we have a number of safe viewing methods. The best viewing method is the one that we handed out with the glasses. Now you probably remember these pinhole projection methods that were taught to you in school, where you take a shoe box and you put a pinhole, maybe a large hole and then a piece of foil and then put a pinhole in it. The problem is that if you try this in real life, you will find out that the projection, it's such a short distance that the projected image is about 1 millimeter. It's very, very tiny. So one thing that you can do if you have some kids or grandkids, or if you're a teacher with students, you can build the same concept but with a longer tube. So instead of using a square box, I'm using a longer tube. In one end, I put a piece of foil with my pinhole. In the other end, I have a piece of white paper and then a piece of foil over that, just so it's completely opaque. And then I put a little window here. You then place this on your shoulder, like a rifle right on your shoulder, and you look down through here with the sun at your back. You can't get any safer than that. And it's really relatively easy. You look at your shadow, you get this until the shadow is as short as possible, and then you'll see a projected image of the sun. The nice thing about this, if you're doing this with kids, then kids can decorate this to their heart's content, put stickers on it. So it's a really nice, safe way of viewing the sun. Even with this, though, the image is very small, about a quarter of an inch. But it's a whole lot better than the shorter box. You could get a larger image if you had a really long tube, but that might get a little difficult to handle. There are some advanced projection methods. If you're an astronomer and you have a telescope, and you can see the issue with this, you have to be very careful with this. You want to make sure that nobody looks through that telescope. Instant eye damage. But you actually project the sun through the telescope onto a card. This is essentially what Galileo did to see sunspots on the sun. Now you'll notice this cardboard shade here. This is now within the shadow of this. That makes it darker and then easier to see. Again, the only issue with this, you have to stand there the entire time. You always have to aim it unless you have a mount that's tracking the sun. But you always have to aim it, but you always have to make sure that no young person comes up and looks through the telescope, because it would be instant eye damage. There are some new safe methods. Now, the telescope here I know is funny looking. This is an old Edmund Scientific Astroscan. If anyone is into astronomy, they've kind of just brought these back again. But this is the device. The guy calls it a sun funnel. You can just Google sun funnel and find this. And all this is an eyepiece. He connected it via a pipe clamp to a funnel from Walmart, a piece of plastic on the end with another pipe clamp, and then he's just projecting that image. Instead of projecting it onto a piece of paper, it's projected onto the rear, so it's a rear projection of the sun. Great idea, great idea. And then you're going to get a nice 4-inch, 6-inch size sun. So very, very safe. Then we have the solar glasses, and a lot of times you'll hear people talking about using welder's glass. And it will work, but here's my only issue with welder's glass. There are a number of different filter shades, and I just don't want people to think that when you say welder's glass 14, it means welder's glass. Every shade is different. So as long as you're using welder's glass 14, then you're fine, but any of these others are not good. So I kind of play it safe and just say, hey, these solar eclipse glasses, they are everywhere now. You have pairs in front of you right now. Libraries, strangely enough in Omaha there aren't. In Bellevue, the library there is giving away free solar eclipse glasses. If you are a teacher or you know any teachers, the NASA Nebraska Space Grant is giving away glasses. Actually, the Omaha Public Schools, as soon as the kids get back to school, every single student in OPS, every single teacher and staff member will have a pair of solar eclipse glasses. Solar filters for binoculars and telescopes. So you'll see, this looks very similar to the solar eclipse glasses we passed out. It's just a little bit larger. It's the same type of film material. It's a mylar film, double aluminized. It blocks out 100% of the UV, 100% of the IR, and then it lets through it blocks 99.999%, lets through 0.0001% of the sunlight. So it's like a pair of super sunglasses and allows you to look at the sun safely. Well, we have a larger filter here that goes on the objective of a regular telescope. So that brings up a good point. You do not put on these glasses and then take your binoculars. That's a big no-no, because now you have a larger area. Those glasses were made for unaided eye viewing, and it will burn your retina. The only way you can use these filters on a telescope is if it's on the objective. It's on the large end of the telescope or of the binoculars. These are available. You can buy just the filter material and kind of cobble your own shade together, or you can buy these ready built for $60 to $100 depending on the size of your telescope. And then last but not least, there are specially made solar telescopes. This is a hydrogen alpha solar telescope. H alpha is a very narrow bandwidth of the electromagnetic spectrum. Instead of this, which allows you to see the photosphere of the sun, this allows you to look at the chromosphere of the sun. And with that, we can see solar prominences, we can see spicules, granulation, solar flares, all sorts of amazing things. But even this little guy here is not inexpensive. There are larger ones, and their price really skyrockets. Yeah?
Several questions, and
Sure.
one you obviously will not bring up. First, I want to ask you, if I looked at that, would I be able to see sunspots, or is they too small? Or is that
That's a great question.
Does it have amplification?
Let's use both of these. Sunspots are on the photosphere. So this would be technically better for looking at sunspots. Sunspots can range in size from relatively small. Of course, even the small ones are about the size of the Earth. They're really big. But from very small to very large. And with this filter here on a telescope, easy, piece of cake to see sunspots. And it's absolutely gorgeous. This one here, the chromosphere is actually on top of the photosphere. The reason we don't see the chromosphere is because, you know, my analogy that I tell my students is it's sort of like the screen on your, if you have one of these protective screens on your phone. I have this protective screen on my phone, and I can see the screen. I can see all the scratches and everything on that protective screen. But the moment I turn on this, I don't see that protective screen anymore. That's because it's brighter. So we're seeing the photosphere behind that screen. The chromosphere is on top. This allows you to see the chromosphere. So can you see sunspots with this? Yes, but not as well as with the visible filter. But yes, you can see sunspots with this.
And
if there are some.
Yeah. I'm sure a lot of young kids and some 20s. The question is, a lot of people will try this, and I want to know if it'll work. They'll take their cell phones, not look at the sun, but they'll record it on there. Will it ruin the cell phone?
Will it ruin the CCD imager? Well, probably not, but I wouldn't try it. Now first, let's just talk about the effective size here. There is something called, and I'm going to go off on a tangent here. There's a wonderful illusion called the moon illusion, and I know everybody's seen it. You may not have realized you've seen it. Now remember when I said earlier that the moon is only a half a degree, a half of a pinky? You probably thought I was mad because, and I ask my students, I go through this, I say, this is 1 degree, this is 5 degrees, this is 10 degrees, this is 15 degrees, and this is 25 degrees. How big do you believe that you have seen the moon? Maybe on the interstate or out camping and you've seen the full moon. How big do you think you've seen it? And most people say they've seen it about as big as their fist. Some people swear they've seen it about 25 degrees. Well, there's this psychological effect called the moon illusion where your brain is trying to compare the size of the moon to things that it knows, like a water tower. This happens a lot. When there's a water tower and the moon's right next to it, you're driving down the interstate, you look over and you notice that the moon looks like it's gigantic. It must have fell out of orbit. It's coming towards the Earth. And then you go over a hill and there's the moon again. All of a sudden, it looks small. A lot of times people try to take a picture of the moon. They take out their, oh, the moon's so beautiful right next to the mountain, I'm going to get a picture of that snap. And then they look and they're like, what the? The camera's not fooled. It looks, because of the wide angle of this lens, that half a degree looks like a dot on there. So you, as far as running the phone, I wouldn't test it. You might hurt that CCD imager, but we're talking just a very, very tiny spot. You're not even going to, you won't be able to see any difference in brightness, maybe until totality. So if you want to photograph the sun safely, well, anytime other than totality, you'll need to have a filter. And you'll need to have at least a 400 millimeter lens on a DSLR. 400 to 500, so we're talking a pretty long telephoto lens to get an appreciable size. That will allow you to see the disc and allow you to see the corona as well. But you do need to be careful. That will damage your CCD imager or your CMOS sensor easily unless you have the filter. Then you can take that off during totality. So those were some fantastic questions. Any others? Yeah.
During totality then, you don't need the protective.
That's right. That's the one time you can take it off.
And then binoculars or not?
Sure. Okay. You could use, but you better be careful, right?
Yeah, really
you better know
yeah.
when that's coming off. It'd be better to just use your camera's imager at that time. But again, you still need to be careful. All right. So let's go ahead and pull out our glasses there. I have 2 different sets that I give away. One set is from Space Grant, the other set is from a group called Mega Movie, and I think those are the ones that you got. And you'll notice, again, you will not see anything unless you're looking at the sun or unless you're looking at maybe the filament of a light bulb. You need to have something extraordinarily bright. So when do you need to wear the glasses? Well, it's easy. You need to wear the glasses during the eclipse, during the entire eclipse, partial eclipse, near total where you might see the diamond ring, even during the diamond ring effect, you need to be wearing those glasses. The only time you take off the glasses is during a total eclipse, and you will see, I know I've said this 100 times, but you will only see a total eclipse if you are within the path of totality. If you're here in Omaha, you're going to need to wear those glasses the entire time. But this is the only time that you would not need to wear those.
How dark would these compare to a welding helmet shade?
14.
The 14 was probably, I used to sell working at welding helmet, or 12 to 14 were common for arc welding.
Yeah. And so that's going to be about the same, probably approximately the same as the number 14. The thing to really to really push to kids is that you can't put on maybe 10 sunglasses. You know, it doesn't work because IR, UV. Maybe not as much IR, but UV is going to go right through those things, and so you don't want to do that. This will work. You'll also notice on the glasses we're talking they're cardboard. That's why I put them in the envelopes to protect those, and that film is very, well, it's very sensitive. So before you use them, you'll want to make sure there aren't any rips or any pinholes. Yeah.
So my coworkers here in town are going to be in Omaha. How much of a percentage will it be in Omaha?
It's about 98.5%.
So will it get fairly dark then in Omaha?
It will not get fairly dark. You will notice it. You will notice a dimming, but it doesn't get dark unless you're within the path of totality. So it is, like I kind of joked, it is the difference between night and day. Yeah, there will be a difference there. Okay, we have a number of fantastic events. We'll wrap this up here. Well, actually, I've got one more thing to talk about once we get through this. There are hundreds, well, dozens and dozens of small events, but there are a handful of very, very large events going on throughout Nebraska. Alliance at Carhenge. Perfect place, right? Scotts Bluff, and then across the entire state. But let's just talk very quickly about the ones that are a little bit closer. Yeah.
Okay, you're going to be in Grand Island. What will be your time?
I will get 1 second of totality more than Beatrice. Woohoo! Yeah. But we decided on Grand Island some time ago, and I'll tell you one. And I usually don't mention this, but one reason Nebraska is so popular for this eclipse is because we have 250 miles of interstate within the path of totality. So these guys that are serious about seeing the eclipse, they're not going to a place. They're on the road, they're mobile, they're ready to move. If the clouds come in, they're ready to get in their car and take off. And speaking of which, it's going to be very congested, very busy, and even a little dangerous too. There will be some very distracted drivers, you know, looking out the window, so you got to be very careful if you are on the road traveling to a location. And the best advice I can give you is get there early, get there very early. So Grand Island has the Gem Over the Prairie, the Stir Museum. In Lincoln, even though it's right on the edge of the path of totality, Haymarket Park, the Salt Dogs baseball team is actually having a baseball game during the eclipse. So as the eclipse is going on, they have the game, and at totality, then they're taking a break so everyone can enjoy the eclipse, and then they'll go on with the game. There's also a science competition, some great lectures and some talks there in Lincoln. And then in Beatrice, of course, this is the granddaddy at Homestead National Monument of America. Bill Nye the Science Guy, also a number of NASA scientists. There'll be a number of different activities going on there at Homestead, and a few other parks. It's not just Homestead, a few other parks around the Beatrice area. This is a quote-unquote official NASA viewing location. This is where you need to go, Eclipse. Wasn't that clever? Nebraska Eclipse, Eclipse17.com. This will give you information about all of the events that are going on within the state. because I just mentioned the things that are going on the day of. A number of these locations are having lectures, having talks, having programs leading up to the eclipse as well. This site will give you information about those. So people wonder where I'm going to be. I already told you I'll be in Grand Island, and the reason I'm in Grand Island is I'm launching a high-altitude balloon from Grand Island. My wife and I are the co-leads for the NASA Nebraska high-altitude ballooning program, and on a very regular basis we launch essentially weather balloons. The only difference is we have scientific payloads that go up. Last Saturday, the Saturday before that, we've launched it. This is a picture that I took last weekend from our high-altitude balloon launch. And so now this curvature is a little bit of a fib. This is the fisheye lens effect. But even if we didn't have that fisheye lens effect, there would be just a slight curvature there. And we can see the atmospheric limb of the Earth. We are about 19 miles up. We are between, it kind of depends, how high did this one go? 93,000 feet. This balloon went 93. So we are 3 to 4 times higher than any aircraft are flying. We are extraordinarily high. Did you have a question?
Well, I was going to ask you how high, but you just answered that.
So very, very high. This is an area that is colloquially called near space, not because it's near to space, but because the environment is nearly identical to the environment in space. We're talking -40 to -70 degrees below zero, nearly a complete vacuum. We've launched, this last balloon flight was number 63. That's how many balloon launches we have done. We have a 100% success rate because we track these things and then we go and get the payloads. And I'm a firm believer in multiple systems, not only redundancy, but multiple redundancies. So I have a tracking system. I then have a backup. I use APRS as a backup. I also have satellite transponders as backups for my backups. And then if all else fails, I have a sign on everything that says, "Reward if found, please call." And we've had to rely on that as well. Well, nearly a year ago, about 55 teams, we all got together in Wyoming, and we built a number of different payload packages. This is what one of the payload packages looks like here. I've got a Raspberry Pi computer system in there along with a Raspberry Pi camera, and there's also a Iridium satellite modem inside there as well. There's our Iridium satellite modem is on the back side, the battery power for that, and then we built an entire tracking system. The difference between this and anything we've done before is that all of our video, we always put cameras on these balloons. And by the way, I'd love to come back and talk to you about our high altitude ballooning program. I'm just kind of talking briefly about this. But we always have cameras on our balloons, but we have to go and get the cameras and get the little memory cards. This is different. We are transmitting live video down to our command centers. This is unprecedented. 55 teams across the entire United States are going to have live video content being downloaded on these balloons. Here you can actually see our little tracking system there. The Iridium modem uploads the GPS coordinates for the balloon to the internet. That then comes to our computer, to our tracking system, and then the tracking system with a couple different antennas on there then get the down feed of the video and the still images. People have sent high altitude balloons within the path of totality of an eclipse before, but nothing like this, where we have live video and we have 55 teams across the entire United States. People will be able to go to streameclipse.live. They will see a map, and I'll show you a picture of it. You will see a map of the United States, and you can choose one of the little glowing circles and then see through the eyes of that particular balloon. Absolutely incredible. Yeah?
You said your beaming signal back down there. What frequency are you
we are using 2.4 gigahertz is connecting the pods. We're using, I think, 900 megahertz. So we have a number of teams, 17 teams up here, 4 teams in Nebraska, 2 in Grand Island, 1 in Beatrice, 1 in Scotts Bluff will be launching. But these are the number of teams throughout the entire United States. What was nice is that we didn't have to go, we're just moving down to Grand Island. Other people had to converge to these different locations, and we'll be launching these balloons. This is during our test, this is what it looked like at least. And we click on this, and then we would be able to see, I put this image in here. The actual image was of a lake when we were testing this. But you will see something like this where we're not looking at the eclipse, by the way, we're looking at the shadow. As the shadow passes across us. And you will be within the shadow, and you will see light on either side. We'll be so high, you'll be able to see the edges of totality. Here are some other very important links. We've already mentioned Eclipse 17. This is NASA's site, eclipse2017.nasa.gov. Wonderful, wonderful website with, my favorite is a interactive map that you can click on the map and it will show you all the details on when the eclipse is happening, the length of the eclipse, everything. But this will also give you information about events, if you're looking for safety tips, everything. And then this is also another wonderful site, greatamericaneclipse.com. I'll leave that up here momentarily. Yeah.
Is there any coordination of NASA with the International Space Station while the eclipse is going on?
Not a good path.
Yeah, do you know anything?
We actually checked out what the passes were going to be,
Yeah.
because we were going to be down there and NASA's going to be right next door. And there were no good ISS passes during the time.
Okay. So they probably will not have a good view. we're in better shape.
Not in the right place.
Yeah. Got to be in the right place at the right
But for
time.
them,
Yeah.
it's even more rare.
Right, right.
Yeah.
They're moving so quickly, right? They'd be in and out of it in a matter of seconds. And I can bring that back up again. Well, on behalf of NASA Nebraska Space Grant and the Branched Oak Observatory, thank you very much for your attention. I know we've covered a number of questions, but were there any other questions that maybe we didn't get to? All right. Well, thanks again, everyone, and do be sure to visit us out at Branched Oak Observatory in the future. Just check out our website or our Facebook page for future events. We have the next big event is on September 23rd. We have our Starbecue, and that is half barbecue, very clever name, half barbecue, half what we call star parties. We'd love to see you out there. Yeah.
What size of equipment do you have out at your observatory?
We are slowly building. Right now we have a roll-off observatory, and we've just built a dome observatory that is not, doesn't have the instrument in there yet. In the roll-off observatory we have a 7-inch Maksutov Aksarben. We have a 6-inch apochromatic refractor, so it's about as good of a refractor as you can get. We'll have a few others. We have an 11-inch Schmidt-Aksarben in there as well. And then we drag out telescopes. We have a 14-inch Dobsonian that we drag out. And then, of course, local astronomers come out. In the big observatory, once it's ready, they'll have a 14-inch Schmidt-Aksarben in it for a short period of time.
Now, I've been out to Meade. They have a good-sized scope out there.
Yep, I do those. I manage the Meade telescope. That's a 29-inch telescope out there. Unfortunately, it's kind of fallen, kind of in disrepair. It used to be the research telescope for the University of Nebraska at Lincoln, and right now we're trying to bring it back to its glory days. We're trying to get it to talk to modern computers, get the mirror cleaned up, maybe in the future even get it resurfaced, and then it will be back and up and working again. We do try to have general public open houses out at Meade Balin Observatory twice every semester, so about 4 times a year. So be sure you watch for those as well. Local astronomers will set up telescopes, and we'll have some students setting up telescopes outside, which usually give you a better view than the big scope inside. But I'll tell you, seeing that big telescope is something else. 29 inches this way, but the length of the telescope probably goes from the wall to my hand. That's how long the telescope is. It's really a very impressive telescope. All right. Thanks again, everyone. Thank you.
Thank you.
Oh, if you don't mind, could everyone put on your glasses and then give me a thumbs up? This is how I know that everybody's ready for the event here. Okay, we'll take a few. Okay, I'm going to do a pan here.
No.
You can't see it, our dang thing, can you? I'm going to take one more. Okay, thumbs up. All right, thanks everyone. Wonderful. I'll be putting that on Facebook tonight. So if you're a fugitive from the law, let me know and I'll blur your face.
Which Facebook page, Branch Oak or?
That will be on Branch Oaks.
Okay.